Okay, Deltamath part 3 for module 4. Going to start off with simplifying basic cubic roots. So first example we'll look at is the cube root of 125. This is one you could do on your calculator pretty easily. Cube root of 125, that'll come out to just 5. But basically what you're going to be doing for most of these is looking for cubes. And cubes are basically made by cubing things. So 1 cubed, 2 cubed, 3 cubed. That's the thinking that's involved. So the first cube, 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4, 5 cubed, 6 cubed. That's probably as big a list as you'll need as for the numbers. And we also have cubed variables, so x to the third. Always starts with x to the third and then goes up by multiples of 3. So the next one is x to the 6th, x to the 9th, x to the 12th, 3, 6, 9, 12, 15, 18, 21, 24 is the highest cube variable exponent I saw. But basically, if you've got 125, which is a perfect cube, so the cube root of that would just be 5, just like the cube root of 8 would be 2, cube root of 27 would be 3. Look at some more examples. Number 2, the cube root of z to the 24. And we're looking for cubes since we've got a cube root. And z to the 24th, that's equivalent to x to the 24th. So it is a perfect cube. And then if it's a perfect cube, exponent, we don't necessarily do it as if it's not an exponent, but you're just going to divide by the index. The index is 3 in this case, so 24 divided by 3, we end up with z to the 8th. In some cases, in these first 2 examples, we've got numbers underneath the radical that are perfect cubes. If it's not a perfect cube, then we're going to rewrite it a bit, and we'll look at some examples like that. Number 3, cube root of 189. And if we look at our cube list, we don't have 189 anywhere on that. So what you want to do instead and see if there are any cubes in 189. And let's see here. If you do 189 and divide it by, we'll say 125, that's not going to work out. Comes out to 1.512. If you do 189 and then you divide that by 64, comes to 2.95. If you do 189 divided by 27, that comes out to 7. So I'm just going to rewrite this as 27 times 7, which is still 189, but we can see our perfect cube there. And I'm going to put a line through the 27. The cube root of 27 is 3. And then the 7 is not a perfect cube. We're just going to leave that inside. Okay, so just to recap, we rewrote the 189 so that we could see if any of these cubes go in. 27 did, so we rewrote this as 27 times 7. Cube root of 27 was 3. One more example for this first segment. cube root of c to the 23rd. So here we're talking about variable exponents. 23, if you look over here at our list, and hopefully you'll keep this, you'll make a list of cubes and then just keep it at hand so you can kind of reference it. But c to the 23rd is not over here in our variable exponent list, but 21 is the largest one we can fit in there. So what we can do is rewrite this as c to the 21st, which we know is a cube, and then multiply that times c to the second. So c to the 21st times c to the second. This is still c to the 23rd, but the c to the 21st we can take out. You'll do 21 divided by 3, 21 divided by the index. So on the outside, it's going to be c to the 7th, and then the c squared had to stay inside. Next, simplifying algebraic cube roots. Got two examples we'll look at here. Number one, 8x to the 3rd, and then cube root of 216 x to the 3rd, y to the 8th. So if we're simplifying this, we're going to look for cubes. If this was a square root, we'd be looking for squares, but here we've got a 3 in that as the index in that little nook. So we're going to be looking for cubes. So I'm going to rewrite that list: 1, 8, 27, 64, 125, and then 216. So 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, and 6 cubed. Also variables: x to the 3rd, x to the 6th, 9, 3, 6, 9, 12, 18, 21. So inside of this cube root, we're looking for perfect cubes that we can take out. 216 is a perfect cube. X to the 3rd, if you look over here, x to the 3rd is a perfect cube. Y to the 8th, though, there's no y to the 8th in here. There's no variable to the 8th that's a perfect cube. So these two are already perfect cubes. We don't need to rewrite those, but the y to the 8th, we'll need to rewrite that. So I'm going to leave the 8x to the 3rd the same. Put that little 3 in the nook. 216, we don't have to change because it's already a cube. X to the 3rd, already a cube. But y to the 8th, the biggest cube in that would be y to the 6th. So in order to make y to the 8th, y to the 6th, we have to take it times y to the 2nd. So y to the 6th times y to the 2nd. This is still y to the 8th, but we'll be able to take out these three things now. They're all cubes. So we're going to take out the cube root of 216, cube root of x cubed, the cube root of y to the 6th. Keep in mind for the variables, x to the 3rd and y to the 6th, we're just going to divide their exponents by the index. So I'm going to put 8x to the 3rd out there, and then everything that we're bringing out. So the cube root of 216 is 6. And you can do that over here. 1, 2, 3, 4, 5, 6 is the cube root of 216. The cube root of x to the 3rd, so we're doing this one now. We just have to take that 3 and divide by the 3 on the way out. 3 divided by 3 is 1. So this is going to be x to the 1st. Same with the y. Y to the 6th on the way out. 6 divided by 3 is 2. And then the only thing left on the inside is that y squared. And then last, we've got the 8 and the 6 that we can multiply. We've got x to the third and x to the first. That's going to be 4 x's, 3 and 1. And then the y to the second doesn't have anything to go with. And then the cube root of the y to the second that's on the inside. Second example, x to the third, and then cube root of 1080, 1080, and then x to the ninth, y to the 10th. Basically the same process. We're going to look for any cubes in there. So 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed. And that's probably good enough. X to the third, x to the sixth, x to the ninth. That's probably good enough here. So let's see, 1080, if we divide that by 216, that comes out pretty nice. So the 1080, we can make that 216 times 5. The x to the ninth is already a cube, so we don't need to rewrite it, x to the ninth. Y to the 10th, though, the next one would have been x to the 12th. So this y to the 10th is not a perfect cube, but we can write it with y to the ninth times, hopefully you can anticipate what power of y it's going to be. Y to the ninth times y to the first, because these still need to be y to the 10th, y to the ninth times y to the first. But we're going to take out that one. X to the ninth is a perfect cube, y to the ninth is perfect cube, and then the 5 and y to the first are going to stay inside. Cube root of 216 is 6. That's going to be on the outside. When we take out the x to the ninth, you're going to do 9 divided by 3. When we take out the y to the ninth, we're going to do 9 divided by 3 again. And then we're going to write everything that's left underneath. So 5 is left and y to the first is left. On the outside, x to the third and x to the third, we can put those together. I'm going to go ahead and put the 6 out front, and then the 2 x's together give you x to the sixth. Okay, that's it for the second section. Next, we've got Pythagorean word problems. So these are kind of lengthy. They have them in paragraph form in Deltamath. I'm going to abbreviate it just a bit. So we've got a few phrases I want to highlight. One is you start driving west 3 miles. So I'll do that in red. Going to go west 3 miles. Next, they say you turn right and drive 2 miles. So you go west 3 miles, you turn and go 2 miles, and we want to see what is the straight line distance from that end point to the starting point. How far is that distance? So we'll go ahead and call that x. And since this is a right triangle, we can use the Pythagorean theorem, which is a squared plus b squared equals c squared. And since this long one is the hypotenuse, the longest side is always c. So a in this case would be 2. We want to square it. B in this case would be 3. We want to square it. And then C, we don't know what it is yet. 2 squared plus 3 squared equals C squared. 4 plus 9 is 13 equals C squared. Ultimately, we want to know what C is, so we need to get rid of this little 2 here. And the way that we do that is we square root that side. So the square root and the square negate each other, but if we square root the right side, also have to square root the left side, and we end up with C equals, if you put this into a calculator, square root of 13, you get something like 3.60555, and we want to round to the nearest tenth. So the tenth is in the first position after the decimal. So what you're going to do is you're going to look at the number to its right to decide, is that 6 going to stay a 6? Is it going to go up to a 7? In this case, since the number next to it isn't 5 or more, we're going to go ahead and leave that 6. And so our final answer ends up being 3.6. So that's our first example in the Pythagorean word problems. Second example is about a TV. TV is 90-inch diagonal. The height is 63 inches. And it's asking how wide is it? So basically what we have is a rectangle. And we know that the diagonal is 90. The height is 63. And we're trying to figure out how wide is it. So if you think of it in terms of just half of this, this is a right triangle. So we can use Pythagorean's theorem. A squared plus B squared equals C squared. And in this case, the 90 is our C. It's our hypotenuse. It's the longest side. So B, let's say we don't know A. Well, actually, it doesn't really matter. Either of these sides, as long as you've got C right, 63 can be A or B, X can be A or B. Let me go ahead and make this B. So we'll let 63 be A. B we don't know yet. So 63 squared is 3,969. And then 90 squared is 8,100. Trying to get B squared by itself, so we got to get rid of the 3,969. We'll subtract that. Got B squared equals 4,131. And then remember, we want to ultimately know what B is, so we need to get rid of this 2 here. So we'll square root both sides. That gets rid of the 2. And we're left with B equals whatever the square root of 4,131 is. So B equals 64.2728. And remember, we want to round to the nearest tenth. So we're going to underline the 2. That's the number that could potentially go up or stay the same. Since the number next to it is 5 or more, that means the 2 is going to round up. Okay, number 3, the area of a rectangle is 380. Its length is 20. Find the length of the diagonal. So again, like I said, this is in paragraph form and you're picking out these bits of information. They're not going to give you a whole lot besides what I've written here, but it is going to have a few more words. So I'm going to go ahead and draw a rectangle. Not a perfect rectangle, so you have to use your imagination a little bit. But the area is 380, length is 20. And we're going to try to find the length of the diagonal. Okay, so part of the problem is we don't know what the height is, but area, this is one thing that you will need to know. Area equals 380. And the way that we figure out area, I'm just gonna break this down as we go. Area is length times width. Area is length times width. So saying A equals 380 is the same as saying length times width is equal to 380. And they do tell us the length is 20. So for the length, I'm just going to replace that with 20. We're multiplying length and the width. So 20W equals 380. And then what we want to do is figure out the width. So we're going to divide 20 on both sides. And we end up with W equals 19. So that's not the answer we're looking for, but it helps get us there because it tells us that this side, the width, is 19. And if you recognize that the shape of half of this rectangle is a triangle, and it's a right triangle that we can use the Pythagorean theorem on, a squared plus b squared equals c squared. C is going to be the long diagonal, but a and b are going to be 19 and 20. So a is 19 squared, b is 20 squared, and then c, we don't know yet. $19 squared is 361, 20 squared is 400. I'll continue that over here. So 361 plus 400 is 761. So C ends up being 27.586. Remember, we're rounding this to the nearest tenth. So you want to underline the 5 and then look to its right. Since the number to its right is 5 or more, we're going to round that 5 up. So C ends up being 27.6. Okay, so moving on to number 4. We got 6 examples in the word problem section. Number 4, some phrasing. We've got a 37-foot ladder. You'll have a couple ladder problems. We'll look at another one right after this. 37-foot ladder. The bottom of the ladder is 22 feet from the bottom of the building. So it's resting against the building, and the bottom of the ladder is 22 feet from the bottom of the building. And we're asked, how tall is the building? So we got this ladder that is 37 feet resting against the wall, like you can imagine. Something like that. And the distance from the bottom of the ladder to the bottom of the building, this is 22 feet. And we're trying to find out what this length is. And this is a right triangle here. Hopefully you recognize that if this is the right triangle, then that means 37 would be C, and then this would be A, and this would be B, or vice versa. This could be A, this could be B. But you have to make sure the 37 is C. So I'll go ahead and let X be A. So we've got A squared plus B, which is 22. And then C, which is 37. Make sure you square all 3 of those. Okay, so A squared plus 484 equals 1369. We do want to get the A squared by itself to start with. Square root both sides, that'll get rid of the 2 on the A, and we end up with A equals 29.7489. So rounding to the nearest tenth, we want to look at the number to its right. It's not 5 or more, so that means the 7 is going to stay 7. Number 5, I'll put a little star next to this one. Of all the ones that you'll see, this one will probably be maybe the trickiest to conceptualize at first. Got a 52-foot ladder. It reaches up 48 feet on the building. And then it says, if Javante pulls it 3 feet, further from the house, how far up the side is it? Okay, so first off, we've got a ladder that's 52 feet. And we've got it reaching up 48 feet. And the thing is, we don't know how far it is from the bottom of the house. So first off, we're going to figure out what that number is. We don't know what this is. Typically, you use an X, but I'm going to go ahead. Since we're doing Pythagorean theorem, I'll just go ahead and call this B. Hopefully, you recognize we've got this right triangle here, and the longest side is the 52. So that's going to be our C. A, we can go ahead and let be 48. We want to square that. B, we don't know what that is yet. And then C is going to be 52 squared. .48 squared is 2,304. B, we don't know what it is. And then 52 squared is 2,704. We want to get B squared by itself, so we need to get rid of the 2304, so subtract it. And we end up with B squared equals 400. Square root, the 2's gone. We're left with B equals 20, okay? So we'll have to go a little bit further with this. It's not done yet. So it does say Javante pulls it 3 feet further from the house. So how far up the side is it? So we can't go with the 48, even though initially it was 48 feet up. We're going 3 feet further. 3 feet further. So that 20 feet, we're going to pull that, extend that to 23 feet. So now what we've got, we don't know what the 48 is now. So I'm going to redo this. The ladder is still 52 feet. The ladder hasn't changed the length at all. But now on the bottom, it was 20. Javante's pulled it an extra 3 feet. So now we're at 23. And now the thing that we don't know is how high up are we? We don't know what this side is. So I'm going to go ahead and call this, what did we call it before? We'll just call that A. So that's the side that we're looking for. So still using A squared plus B squared equals C squared. And then we're just solving a basic Pythagorean theorem problem. So A, we don't know. B is going to be 23. And then C, 52. So 23 squared is 529, 52 squared, 2704. We want to get A squared by itself, so you got to get rid of that 529. So that's gone. Bring down the equals, A squared all alone on the left. And then we've got 2175 on the right. Square root. And A equals 46.6368. $43.6368. So are we going to round up or keep it the same? So since the number next to it isn't 5 or more, we're just going to keep it the same. And this kind of makes sense, you know, if it was 48 feet to begin with, and then we brought it out a little bit further, the height did come down a little bit, but not too much. It was 48 feet at the beginning. Now it's at 46.6. Okay, so number number 6. The altitude from the vertex of an isosceles triangle cuts into 2 equal segments. Okay, so that's one of the phrases. Also it tells us that the altitude is 29 inches. The base is 18 inches. And we're looking to find the perimeter. Okay, so an isosceles triangle, just to give you an idea, has 2 sides that are of equal length. So just imagine that this left side and the right side are both the same length. They do tell us that the base is 18 inches. So 18 there. The altitude, I'll go ahead and do that in red. The altitude just from the top to the bottom, this is the vertex point at the very top. So the altitude, the height of the overall thing is 29. And it does say it cuts into 2 equal segments. So when we get to the bottom there, that 18 is cut into 2 equal segments. We're dividing it in 2. So that means that this distance from here to here, from the edge to the middle, has to be half of 18, which is 9. And that means the other side is 9 also. Okay, so we're meant to assume that it lands at a perfect 90-degree angle. The altitude comes down that way. So we've got, basically, if I can highlight this, we've got a right triangle there. We can figure out what x is, and we can figure out what the other x is. And then the perimeter, once we get to that, that's a little ways ahead, we're just adding up all the outside. Let's say if we find out x is 5, we've got 5, 5, and 18. We'll add those together, and that'll give us our perimeter. Okay, so for now, just you're going to use the Pythagorean theorem, a squared plus b squared equals c squared. Make sure you notice that the longest side is going to be the unknown side. So I'll go ahead and we'll treat it like it's c, even though I'll leave it called x. But a and b are going to be the sides of the right triangle that are not the longest, not the hypotenuse. So for a, we can call that 29. For b, we can call that 9. Okay, so 29 squared is 841. 9 squared is 81. So add those two on the left, 841 and 81, we get 922. Ultimately, we want to know what c is, so square root. So that gets rid of the square roots there, or the square. So we've got c equals 30.36445. Probably, by the way, I talked to somebody about this earlier, but it does want you to round to the nearest tenth. But this is at the end. So don't round to the nearest tenth at this point. That number actually does go further than this, you know, so you could put more decimals on there. But as long as you've got 4 or 5 digits after the decimal, you should be okay. But what we're going to do is we're going to use this now for our x values. So we've got, if we're doing the perimeter, and like I said before, the perimeter is the entire distance around. If we know what x is, we add that to that other x, and we add that to 18, and that gives us our entire perimeter. So if the one side is 30.36445, and the other side, so we've got the 1 there, we've also got the other x, so 30.36445, and then we're also going to add 18 to that. That's this bottom one. Okay, so let's see what that gives us. 30.36445 plus 30.36445 plus 18, and we should get 78.7289. And this is the part, when we get to the very end, the perimeter, that we're going to round to the nearest tenth. So the 7 is in the tenths position. We look at the 2. We know the 7 is not going to change. It's just going to stay a 7. And that ends up being the perimeter for that. Okay, so that's the last example in that section. And we've got just 3 more, 1, 2, 3, 4 examples to look at. Radical equations, level 1. So we've got 4x plus 40 plus 6 equals 10. Be careful when you're copying this. This square root symbol only extends over the 40. It doesn't go over the 6. So be careful when you're copying this that you don't do that, that you don't accidentally bring that line across the 6. So you might be tempted to put the 40 and the 6 together on the left, but actually we want to get the radical by itself first. So what that means is we want to get rid of that 6. Subtract 6 from the left, also subtract 6 from the right. So 6 minus 6 is 0. Bring down the equals. On the left now, we've got that square root of 4x plus 40. On the right, 10 minus 6 is 4. And in order to, let's do this on the next step. So I'm just going to copy that. And then if we want to get the x all by itself, we'll have to get rid of the 4, the 40, the square root. Start out by getting rid of the square root. By squaring both sides, the square root and the square cancel each other out. Square both sides to get rid of the radical. This is something that we'll do a few more times on the examples coming up. So that leaves us with 4x plus 40, and then 4 squared. Be careful you don't put 8 on that. 4 times 4 is 16. And then we just want to get the x by itself. So subtract 40. We got 4x equals negative 24. Divide 4. And we end up with x equals negative 6. You do want to check these answers in the radical equations. check radical, check the radicals answers. Really all that means is you're just going to plug in this -6 back into the original equation. So that square root of 4x plus 40 plus 6 equals 10. And we'll see if it works. Plugging that in for x. So we've got 4 times -6 plus 40 plus 6 equals 10. 4 times -6 is -24 plus 40 plus 6 equals 10. -24 plus 40, positive 16. Square root of 16 is just 4. And then so we do end up with 4 plus 6, which is 10, equals 10. So that works out. In some cases, you might have to throw out some of these answers. By the way, -6 is the answer, and you'll enter this in the computer as with the squiggly lines and then -6 in the middle. If we ended up with something like -10 equals 10, obviously that's not true. So you would leave out the -6. If you left out the only answer that you had, you just want to put in the squiggly lines and then nothing on the inside, just to show that the set of solutions is empty. There's nothing that works. Radical equations level 2. So square root of 2 minus x equals x minus 2. So just like the last one, we do want to get the radical by itself. And on the last one, we had this plus 6 along with the radical that we needed to get rid of, so we subtracted 6, and then we had the radical all by itself. On this equation, if you look at just the left side, we've got the radical all by itself. So this step here, get radical by itself, we won't need to do that here. So what we'll want to do after we've done that, or after that, anytime the radical is by itself, you can go ahead and square both sides, and that gets rid of the radical. Squaring a square root eliminates the square root. So square both sides. So on the left, we're just left with 2 minus x. On the right, though, you'll need to be careful about this because a lot of times people will just square the x and put x squared. They'll square the 2 and put 4. But really what you're doing is you're squaring that whole x minus 2. So this should look like this. X minus 2 times x minus 2. Just like if it was 4 squared, it'd be 4 times 4. And anytime you've got, this is what's called a binomial, 2 terms times another binomial, you're going to go ahead and FOIL. So that means first times first, the outers, multiplying all these, by the way, and then -2 times x, also -2 times -2. So I'm just going to do that next. X times x, x times -2, -2 times x, and then -2 times -2. Negative times a negative is positive, and then 2 times 2 is 4. Got some like terms we can put together, so I'm going to do that really quickly. So 2 minus x, not doing anything on the left. So -2x and -2x combine to make -4x. And most of the equations we look at, if we go back just a little bit, we won't talk a whole lot about this, but this is what's called a linear equation. You've got a power of x, but the highest power is just x to the first. Down here, we've got what's called the quadratic equation. We've got x's, and the highest power of x is 2. This is quadratic. We're going to set equal to 0, which means we're basically going to bring everything on the other side over to the x squared. So we want to bring over the 2, subtract it. We also want to bring over the negative x. We're going to add it. Make sure you do that on both sides. Subtract 2. I'm going to put that underneath the 4 since they're like terms. Also add x underneath the x term there. So on the left, both things canceled. We can go ahead and put a 0 there since there's nothing else there. On the right, bring down the x squared. Negative 4x plus x. Remember, this is a 1x. So negative 4 plus 1. And then 4 minus 2. Okay, and there's a few different ways that you'll be able to solve this once you get to this point. One way is the quadratic formula, which we'll talk about a bit down the road. The fastest way, though, is going to be by factoring. And you may not have had a lot of experience factoring yet, but basically, if you've got a trinomial, 3 terms, you can put that into 2 parentheses, 2 binomials that multiply to be that. And generally, the first things, let me do that in a different color. The first 2 things multiply to be the x squared. So that's generally going to be the easiest things. 2 things that multiply to be x squared are x and x. Then you're going to want 2 things that multiply to be 2 and then add to negative 3, which is this middle term. So they multiply to 2 and add to 3. Not a lot of things that multiply to be 2, 1 and 2 are the only things that multiply to be 2. So if they're going to multiply to be positive 2, they either need to be positive 1 and positive 2, or another way you can multiply to make positive is to have both of them be negative. And since they're meant to add to a negative number, we might determine that they both need to be negative. Negative 1 times negative 2 does give you positive 2. Negative 1 and negative 2 also add to be negative 3. So we can go ahead and put those in, negative 1 and negative 2. And then basically this tells us that x equals positive 1. And here x equals positive 2. And I'm skipping a little bit of a step there, but just to explain to you what's going on here. If you imagine both of those circles multiplying, so the thing on the left, this whole thing multiplied by this whole thing gives us 0. You can't multiply 2 things and get 0 unless one of them is 0. One of these circles has to be 0. So we might say that x minus 1 equals 0 or x minus 2 equals 0. Add 1. Add 2. X equals 2. And again, on these radical ones, you'll want to go back to the beginning, substitute in those values and see if they work okay, because we've got positive 1. We've also got positive 2. We'll go ahead and substitute 1 in and see how that goes. I'll do this in red. Square root of 2 minus x. And I'll go ahead and use 1. Equals x minus 2. So just plugged in 1 where all the x's would go. 2 minus 1 is 1. 1 minus 2 is negative 1. The square root of 1 on the left is 1. So 1 equals negative 1. That's actually false. So what that means is that 1 doesn't work. And we'll try 2. So we've got square root of 2 minus 2 equals 2 minus 2. Two minus 2 is 0. 2 minus 2 on the right is 0. Square root of 0 is 0. So we end up with 0 equals 0. That's true. 0 is equal to 0. So that means that we can go ahead and put in 2 in our answer. And keep in mind that you're going to put it in like this. If you've got multiple answers, you know, if you had 6 and 3, you might go ahead and enter them in like that. If you had 2 answers, here we just have 1. Okay, last radical equations level that we'll look at. I'm going to go ahead and leave off level 4. Radical equations level 3, we've got square root of x minus 1 equals the square root of 5. Actually, let's go back. Square root of x plus 1 equals the square root of x plus 7. So typically we do want to get the radical by itself anytime we're dealing with radical equations. But you'll notice we have a radical on the left. We've got a radical on the right. The radical on the right is already by itself. So we'll go ahead and start by solving from here. We're going to square both sides. So I'll rewrite this. Square root of x plus 1 equals square root of x plus 7. And we'll square the left, square the right. So on the left, those cancel out. And on the right, you'll need to be a little bit careful because you'll notice that this radical doesn't extend the entire distance. If it did, then we could just cancel the radical and the 2 and we'd be done. But since that radical doesn't extend over the 1, we have to treat this as a binomial. And we're going to do square root of x plus 1 times the square root of x plus 1. And then on the right side, we just have x plus 7. This radical stuff, by the way, might take a bit of practice to get down. So don't be surprised if there's a little bit of a learning curve. But starting out with the square root of x times the square root of x, and just to simplify things for you, anytime you take like the square root of 5 times the square root of 5, you just get 5. If you take the square root of 7 times the square root of 7, you get 7. If you take the square root of x times the square root of x, which is what we're doing here, square root of x times the square root of x, you just get x. Next, taking the square root of x times 1. Anytime you take 1 times something, it's just that thing. So square root of x times 1 is the square root of x. On the inside, we've got 1 times the square root of x. So again, square root of x. And then 1 times 1. positive 1. Okay, so switching back to blue, going to combine some like terms there. Square root of x plus the square root of x. There's some invisible ones in front of both of those, and anytime you combine like terms, square root of x and square root of x, you're really combining the numbers in front of them. So this one is going to be x, not doing anything for that. But 1 and 1 is 2 square root of x. So all I've done there is add like terms. Then what I'm going to do is, now that we just have one radical left, just this one radical here, I'm going to start by getting it by itself. So we want to get rid of the x over here that's on its side. We want to get rid of the 1 that's on its side. So we're going to subtract x. That's going to get rid of it. Subtract 1. That's going to get rid of it. Make sure you do that on both sides. So subtract x. I'm going to put that underneath the other x term. And then also subtract 1. Bring down the equals on the left. 2 square root of x on the right. X minus x, those just cancel out. And we're left with 7 minus 1, which is 6. So still wanting to get the radical completely by itself. So here we would divide, let me do a different color. Divide 2. Those cancel out, and we're left with the square root of x equals 6 divided by 2, which is 3. Rewrite that. So ultimately, we've got the x or the radical by itself. Now we want to get x by itself, so we need to get rid of that radical. It's a square root, so we can square it to get rid of it. Squaring a square root cancels. And x equals 9. And just like the others, we'll want to go back and plug that in. Square root of x plus 1 equals the square root of x plus 7. X is 9, so we're saying the square root of 9 plus 1 equals the square root of 9 plus 7. Square root of 9 is 3. 9 plus 7 here is 16. So on the left, we've got 3 plus 1. On the right, we've got the square root of 16. That's true. So it means it does work. So when you enter the answer in, you just put those squiggly lines and then 9. Okay, so like I said, the radical equations, I expect they might be a little tricky to get down at first. The next examples, I don't think will be that difficult. I expect that you'll have an easy time with them. These are exponential and radical form. Right in exponential form. So we've got 7 in that little nook there. The index is 7, and then we've got x squared. So exponential form just means that we're gonna write this as x, but with an exponent. And what you want to do is put the power on top. The power of x, which is 2 here, and then also the index on bottom. The index is this number that goes in the little nook there. So you'll want to, it's an exponent, so you will want to, I forget what they call it, but where it's raised up. But that's all you've got to do. Put the power of the x on top, the index on bottom. Another thing you'll have to do in this section is write in radical form. So basically all you're doing is you're going in reverse. We're starting with an exponential and we're going backwards into this. And as long as you remember that the bottom number that they give you is the index and you remember that the top number they give you is the power, should be no problem. So if we've got something like x to the 1/3, keep in mind that's the index and that's the power. So the index goes in that little nook. We're going to have x to the first. And generally, anytime you've got x to the first, we're just going to write x. So we'll look at one more example of that. X to the 2/3. Going to change it to a radical. So we want to put the index in that little nook. Index is on bottom, so we've got a 3 there. Underneath, we've got x, and then the power of the x is 2. Okay, so hopefully not too bad. That's it for the notes for Module 4. Email them if you have any questions.